this example involving the flow of current. So if a current of 80 milliamps exists in a metal wire, how many electrons flow past a given cross-section of the wire in 10 minutes? Also, we want to sketch the direction of the current and the direction of the electron's motion. So the fact that we're given is that the current in this wire is 80 milliamps. And we want to know how many charges flow past a given cross-section of the wire in 10 minutes. So we know that current is related to the amount of charge and is equal to the amount of charge that flows past some cross-section in some amount of time. And we know the current and the time, so we can figure out how much charge flows past. So that would be delta Q is equal to I times delta T. In this case, our current is 80 milliamps, so that's 80 times 10 to the minus third amps. And the time that passes is 10 minutes. And so 10 minutes would be equal to 600 seconds. So therefore, we have an amount of charge that flows past any point in our wire of 48 coulombs. So that would be the amount of charge that passes a cross-section of the wire in 10 minutes. Next, we want to sketch the direction of the current and the direction of the electron's motion. Oh, first off, though, before we do that, we want to figure out how much charge in terms of electrons does this 48 coulombs represent. So we know we have 48 coulombs passing, but we want to convert that to a number of electrons. So if our delta Q is equal to 48 coulombs, we know that there's 1.6 times 10 to the minus 19 coulombs in one electron. And so this 48 coulombs represents about 3 times 10 to the 20 electrons. So there's 3 times 10 to the 20 electrons that pass any point in the wire during the 10-minute interval. Now we want to sketch the direction of the current and the direction of the electron's motion. So if we say that this is our wire and it has some electrons in it, obviously not to scale, if the electrons are moving to the right, so if their velocities are to the right, then the flow of the current will be opposite the direction that the electrons are moving. Now, when current and voltage are measured, it turns out that you can measure both of these with the same device. You can measure them both with a multimeter. And during your labs, you'll be making circuits, setting up circuits, and measuring current and measuring voltage. And you'll notice that the way in which you measure current and voltage is different. If you're measuring a voltage drop, your meter will be in parallel to the item that you're measuring the voltage drop over. So if you wanted to measure the voltage across a battery, you would connect your multimeter so that one wire of the multimeter is touching here, the other is touching here. So the multimeter would be in parallel to the battery. In this diagram, and over here in this picture, we're showing how you would measure the voltage across a bulb. So you would put the voltmeter in parallel to the bulb. The electrons could either go this way towards the multimeter or this way through the bulb. So since the voltmeter or the multimeter is in parallel with the bulb, there is the same potential difference across both the multimeter and across the bulb. So when you measure voltages, you always measure in parallel. If, on the other hand, you want to measure current, you need to put your meter in series with the rest of the circuit. You want all of the electrons coming out of the battery to flow through the multimeter and then through the device that you want to measure the current for. So if we want to know how much current passes through the bulb and comes out of the battery, we need to make our multimeter part of the circuit in order to measure current. And something that measures current is called an ammeter because you're measuring amps. So if you're measuring amps, if you're measuring current, the meter has to be in series so that all of all of the current flows through the multimeter, and if you're measuring voltage, it has to be in parallel. So the potential difference across the multimeter is the same as the device you're measuring the potential difference of. Now it turns out that current doesn't flow perfectly smoothly through a conductor. Instead, the electrons kind of generally travel in one direction, but they bop around a lot. They have collisions with the atoms in a conductor, and this creates friction for the electrons. The wire generally heats up, and it creates resistance. So resistance is defined as being the voltage drop across the conductor divided by the current. Typically for a wire, the resistance is very, very small, and for other materials it can be higher. If we rearrange this equation such that the voltage drop across a conductor is equal to the current times the resistance, this is known as Ohm's law. So materials that obey Ohm's law are ohmic, and materials that don't obey this law are non-ohmic. We'll primarily be considering ohmic materials, and you can assume that if we mention a conductor and we give the resistance of a conductor or a resistor, we're talking about something that does obey Ohm's law. So the units of resistance are ohms, and if we rearrange this equation and solve for resistance, you can see that that is equal to a voltage divided by a current. So 1 ohm is 1 volt divided by an amp. So ohms are the SI unit for resistance. If you have a resistor in a circuit diagram, it's represented with a jaggy line, indicating that the resistor is causing issues, causing resistance for the electrons traveling through the circuit. Resistors look something like this typically in real life. There are these little electronic devices that have bands on them, and the bands follow a color code, which you'll learn maybe a little bit about in lab, and this color code tells you the value of the resistance of the resistor. Resistors are used in electronic devices to control the flow of current and to make the current flowing through a circuit either bigger or smaller. Now, the resistance of a conductor depends on its physical properties. So if you want to find the resistance of a conductor and you know something about it, you can calculate the resistance as being equal to the resistivity. This is something that depends on the material that the resistor is made from. Then you also need to know the length of the resistor and the cross-sectional area that the current is flowing through. So let's use these concepts to look at this example problem, where once again we have a neuron, and current can either flow through the neuron down its length, or it can flow out from the inside to the outside of the neuron. So we have here some facts. We know that the diameter of the axon is 10 micrometers, so that means 10 micrometers here. The membrane thickness, so the thickness of the lipid layer, is 10 nanometers. The segment length is 1 millimeter. The resistivity of the axoplasm is 1 ohm times meters. The resistivity of the membrane is 10 to the 8 ohms times meters. And then we want to calculate some things. We want to calculate the resistance of a millimeter length through the axoplasm, and then we also want to calculate the resistance through the membrane, and then the ratio of the membrane to the axon resistance. So first off, let's write down, reproduce this diagram, and then write down once again some of these facts that were given and assign them to variables. So in this problem, we have this axon segment, which is cylindrical in shape. So here is the inside, here is the outside of our axon, and it has some length. So if we, and then I'll draw also the inner surface of the axon. So there are some things that we are given. We are told the diameter of the axon, which would be this distance here. This is the axon diameter, and we know that the diameter of the axon is 10 microns. So 10 times 10 to the minus 6 meters. We also then can find the radius, which of course is half that length. So the radius, which is d over 2, is going to be equal to 5 times 10 to the minus 6 meters. Another thing we're told is the membrane thickness. So that would be this thickness here. So the distance between the inner surface and the outer surface. And so that thickness is very small. It's 10 nanometers, or 10 times 10 to the minus 9 meters. Then we are also told the resistivity of the axoplasm, or the resistivity of the axon. So that's the resistivity of the material if the current is flowing through the middle of the axon down its length. So in that case, the resistivity of the axon is going to be equal to 1 ohm times meters. And then the resistivity of the membrane, so this is for current flowing from the inner surface to the outer surface through the membrane, through that lipid layer. That resistivity is 1 times 10 to the 8th ohms times meters. And we need to figure out what the resistances are for this segment of axon. So first off, we want to find out what is the resistance through the axoplasm. So you can imagine current, so basically the inside of this cell is like a wire, and current is flowing down the inside of the neuron segment. So the resistance through the axon, or down the axon, then is going to be equal to the resistivity of the axon times the length divided by area. So this is the expression we saw in the previous slide, where the resistance is the resistivity times the length of the conductor, and then divided by the cross-sectional area of the conductor. So in this case, the cross-sectional area, well, it's a cylinder, so the cross-section would be a circle, and the area of a circle is pi r squared. So we can rewrite this as being the rho for the axon times the length, and then we divide it by pi r squared, where r is the radius of the axon. So we can put in some numbers for that. The rho for the axon, the resistivity is 1 ohms times meters. The length of the axon, which I didn't write down here, but we were told that the length is 1 millimeter, so it's 1 millimeter in length like that. So then we put that in here. So this is 1 times 10 to the minus 3rd meters. Then we would divide by pi times r, which is the radius, 5 times 10 to the minus 6 meters. And then we would need to square that. So we come up with a resistance for the axon of 1.27 times 10 to the 7 ohms. So that would be the resistance of the axon for current traveling down its length. So next, we want to find the resistance through the membrane. So now current is flowing from the inside of the axon to the outside of the axon. So effectively, current is leaking out of the axon, traveling from inside to outside. So once again, when we calculate the resistance, this time for the membrane, that's going to be equal to the resistivity of the membrane times the length that the current is flowing divided by the area through which it is flowing. Now in this case, the length that the current is flowing from the inside to the outside through the membrane, through that lipid layer. And we know that lipid layer has a thickness of 1 nanometer. So the current has to go only a distance of 1 nanometer in order for the charges to get out of the cell. So this is equivalent to the thickness. And now what about the area? Well, if we're flowing through the membrane, we're going from the inside to the outside, we can do that all around. And so effectively, the inside is, the one side of the membrane is this circle, and then the other side is this outer circle. So we can flow through the membrane at any point along the membrane. So once again, it might be most convenient to figure out this area that the current is flowing through. If we make a cut down the length of the cell and unwrap it like we did before. So in that case, we end up with something that looks like this. So here is our cell just unraveled, cut and down its length and unraveled, so that this is the length, which is 1 millimeter. And this is the same as this surface here wrapped around. And so this is going to be, this length here would be the circumference of the circle, 2 pi r. And the current is flowing from one side to the other through the thickness of this layer. So if you can imagine this as being part of a circuit, you'd have one wire coming in the back attached to the back surface. You'd have another wire sticking out the front, and the current is flowing through this membrane, and it can flow through any part of this membrane. And so the area is the total area of this unfolded membrane, which is going to be equal to 2 pi r, the length times the width, 2 pi r, and then times L. So once again, we can think about plugging in numbers. So the resistance for the membrane is going to be the resistivity of the membrane, 1 times 10 to the 8th ohms times meters, times the thickness of the membrane, which is 10 times 10 to the minus 9 meters. And then we divide by 2 pi times the radius. The radius was 5 times 10 to the minus 6 meters. And then the length is 1 millimeter, 1 times 10 to the minus 3rd meters. So then that's going to give us a value of 3 times 10 to the, or 3.18, sorry, 3.18 times 10 to the 7 ohms. So 3.18 times 10 to the 7 ohms is the resistance of the membrane. Finally, for part C, we need to compute the ratio of R for the membrane divided by R for the axon. So that ratio, R for the membrane over R for the axon, would be 3.18 times 10 to the 7 ohms divided by 1.27 times 10 to the 7 ohms, and that gives us a ratio of about 2.5. So it's about 2.5 times easier for the current to flow down the length of the axon than through the membrane. So here were the ideas that we considered during today's lesson. We looked at how capacitors are devices for storing charge and therefore storing electric potential energy. You define the capacitance of the capacitor as being the charge divided by the voltage across the capacitor. And then we saw that for a parallel plate capacitor, we could find the capacitance based on the physical attributes of the parallel plate system. We looked at how to add capacitors, how in parallel you can just add up the capacitances and the voltage drops across all of the capacitors are the same. And in series, the charge is the same and the voltages add up to give you the voltage of the battery or the voltage of the entire branch. And in order to add the capacitances, you have to add the reciprocals. Then we looked at the energy stored in a capacitor and saw that there were a couple of different equations we could use and you should use whichever one is most convenient for your problem. Then we looked at capacitors that have dielectrics and saw how a dielectric increases the capacitance of a capacitor. Finally, we looked at current as being the rate that charge flows, and saw that Ohm's law predicts how a resistor can be used to control the flow of charge. Finally, we looked at how the resistance is related to the physical attributes of the resistor.